Hi everyone, my name is Yi, and I'm glad to present my solution, which won the second place in this competition for the interactive segmentation. And first of all, I want to introduce our team members. So we have Ziyu, postdoc at Nanjing University, and Yi, postdoc at Ohio State University, and Professor Xue at Ohio State University. In this presentation, I'll walk you through the key components of our solution, and the most important one is global ROI. As we know, in existing methods like SEMath3D, the ROI is cropped at the last point. In this ROI strategy, the organ may be split into several different parts, and we think it is not a good solution as the model cannot get the global context of the organ. And different from these existing methods, we propose global ROI. As shown in this figure, we find the enclosing box of all positive from all positive prompts, and then enlarge the box by a factor, and then we crop and resize based on these prompts. So after this process, the global ROI is expected to include the whole organ and do not include too many backgrounds. And based on our global ROI, we also propose the interaction simulation. In SEMath3D, the strategy is just to compare the last output and get a false prediction, and then select a random point within the false prediction as the next prompt. So if we look into the points generated by this strategy, we can find that many of the prompts are at the surface region of the false prediction, which is consistent with the human behavior and the evaluation protocol. So we're going to design a simulation method that focuses more on the central region rather than the surface region. And meanwhile, we want to make it fast enough for training the network. So our solution is very simple, where we apply a Gaussian filter on the false prediction. So the value at the surface region should be lower than those at the center. Then we can generate the next prompt based on the probability. And meanwhile, we can further improve the efficiency by generating multiple points and averaging their loss. In our implementation, we simulate 6 points per interaction, and we run 5 interactions per training step. So the total will be 30 prompts per training step. And this approach also highlights another advantage of our global ROI. Since the global ROI encompasses the entire organ, so we don't need to recrop the image for a new prompt, and we don't need to run the forward of the image encoder. Instead we just run the image encoder once and followed by 30 runs of the decoder. And we know that the decoder is much faster than the encoder, so our method is highly efficient. As you may have noticed, our global ROI only works when we have enough prompts. For example, if you only have one point prompt, then it's impossible to calculate the global ROI. So we also incorporate a local ROI, which is the same as Vista3D, to deal with the cases that our global ROI cannot process. Our global ROI is developed based on Vista 3D, and we also do some modifications and fine-tune the model. By the way, there is another advantage of our global ROI. We can input all the prompts into the network, all the prompts into the prompt encoder, instead of just using the last one. And our ablation study also showed this can improve the accuracy. And this is the simulation. This is our modification in the local ROI. We propose to adjust the proportion between positive and negative prompts. For example, if we use the local ROI, for example, sometimes the organ is very small, then the points generated by the Vista 3D, the positive point it will be just one or two, and most of them are the negative prompts, which we think is not good. So we propose to generate the first point based on a rule the same as the evaluation protocol. That means the first point will always at the central within the positive label. And then we use the model to do a prediction. Now we have false negative and false positive. And then we generate positive clicks and negative clicks based on a preset proportion. While we expect the global ROI to be very stable, the ROI is estimated during inference could be different from the ROI during training. So to compensate that, we also do some augmentation. During the training, we crop the global ROI first, and then we do the augmentation. We use elastic deformation, and we use random scalings and random translations so that the model can offer an accurate result even when the global ROI is not accurate. We also do some ablation studies. So as you can see here, we start our development based on SAMAT 3D, and which is about 46% on our 1% validation set. And then after we use the global and local ROI, the performance is boosted to 71%. And after we add the augmentation, the performance is about 78. And finally, we achieve 83 on our 1% validation, which is a very huge improvement compared to SAMAT 3D. And here is our results on the validation set. You can see that our model achieves a better performance than SAMAT 3D and Vista 3D that our model is based on. And this is the results of the testing results on the all data check. So our model is worse than an interactive and AIM, but is still much higher than Vista 3D and SAMAT 3D baselines. Here is some visualization of the good cases. And here are some fail cases. So our method is still works not well on the vessel cases. But it is very accurate on the organs like kidneys and livers. Yeah, because those organs are very suitable for our global ROI. And Here are my suggestions for future research. The first one is the switching strategy between global and local ROI. Currently, we simply switching global or ROI, local ROI based on whether a box is provided. It is too simple. And the second one is the evaluation of global ROI. Maybe we can use both prompts and image to evaluate the suitable ROI. So that's all for my presentation. I'll be happy to take any questions.